Great, thank you so much. So I'm very happy to see so many people here today who are willing to weather a literal typhoon to be here. So given that, I want to respect everyone's time and get straight to the questions to our distinguished panelists here so you can hear from the people you're here to hear from. So to start off, I want to ask kind of a general question to each of you to get people thinking about kind of the diversity of life experiences here on stage. You all work in the US today, but you come from all over the world, different parts of the world. Can you talk a little bit about how have your variety of backgrounds, your life experiences shaped your work and led to you being here on stage today? Maybe we can just go around the circle here.
Yeah, so I grew up in a middle-class family in India, and it was without much, ancestral wealth or something. So for me, when I got the opportunity of getting scholarships and the ability to research, I found it extremely positive. So I don't complain much. Any opportunity I get has always been very valuable. I think that sort of a positive attitude has been extremely helpful in going on in my life.
For myself, well, I was born in Malaysia and I come from very humble backgrounds. There were no expectations of what I was supposed to do. I had a very easy, carefree childhood. And all I know is I do love learning a lot. And I come from a family of 9 children.
Wow.
Yeah, and my mother was a homemaker, and seeing her work so hard really instilled work ethics into me. That has really been pivotal to shaping my whole career. And I love biology, biochemistry in school, and was fortunate to get a scholarship to do medicine in our only one medical school in Malaysia then. And then after that, I got an opportunity to go over to UK. And after completed my training, and I wanted to do some research, and I was fortunate to join Sir David Weatherall's unit and was involved in cutting edge kind of global research. And then went to London back again to practice clinical medicine. And then I came to the US, and that's where I've been since.
Yes, I've probably traveled the least distance. I was born in Manhattan, actually, New York City. And the furthest I've traveled in terms of career is Boston, which is 120 miles away. I grew up in a family of, father was a physician, and so I was exposed to medicine very early on. But what I really became interested in is the science behind medicine. I really wanted to understand why do we have disease? What is disease about? And as I sort of came into university experience, I learned that there was a whole new field developing, that is molecular biology, where you could begin to actually dissect in detail, everything that programmed us and everything programmed disease, and that sort of set me on my way.
I was born in South Africa, in Johannesburg, and during apartheid era, and that was enough to convince me I should get out of there. But my real opportunity to get out was that I did an undergraduate in mathematics. After being a keen chess player, I discovered mathematics as an undergraduate, especially abstract mathematics, and never turned back. That it's clear to me that's what I want to do. Big choice for me in leaving, and luckily enough I had opportunities, was to either go to England, which is what most Commonwealth people would do to go study, but I felt that the English system was too specialized, and the American system seemed much broader and more appealing to me. And I went to Stanford to work with a particular guy who was very dynamic and very interactive and very aggressive, and we got on well. And once I arrived in the US, I stayed there and have managed to do what I wanted to do.
Great. Sorry. Let's move this over. So a common theme here is having the room to explore, I think. Dr. Kulkarni, you've mentioned that switching your area of study every 5 to 10 years has been an approach for you, and that can seem kind of frivolous in your search for novelty. Was a quote I saw from you. Do you think this approach has contributed to your success in your field? And do you think that offers any advice that you might have for some of the students in the audience?
Yeah, so I'll first offer the advice and then answer the second part of your question. The single most important advice I'd like to give to young people here who have plans or aspirations to become a researcher is listen to yourself and analyze yourself and take decisions on who you are, not who you want to be. Okay, many times I think, like if you're a physicist, you say, oh, Einstein, Feynman, Fermi, they all sounds wonderful, but you have to know who you really are and maximize on that and minimize on your weakness. Then I'd like to defend actually the bulk, most of science really requires dedication for a long time because you're asking some fundamental questions and the solution may take decades. So I definitely want to tell young people that there's a good reason why many scientists actually choose an interesting problem and go after that. However, when I was young, I discovered that's not who I am. And I personally don't actually have a strong idea of here's a research topic I want to work. I'm very, very curious. I'm curious about anything, and it's just a question of which thing I want to do for that day or for that 5 years. And for me, that's been helpful, partly because I can't work on a single problem in a day. I usually like to think of 5 or 6 things and push them simultaneously. So it's contributed to my productivity. And also, most of my research has been, in some sense, being a sharpshooter. You get into a new field, and all the established people have some ideas, and then you see it in a new way. And I've been quite lucky. Most of the times I've found something new. So I would say that, in summary, yeah, for me, this is my formula. If you're young, figure out your own formula, but critically, not what you simply wish to do.
So on the point of staying dedicated, building on research over time, Dr. Thein, you were an your work, of course, you're being celebrated here today for being an early contributor to recognizing a gene, the role it plays in hemoglobin production, and it came ahead of contributions that Dr. Orkin made. I'm wondering, are there specific contributing factors that you think, or specific strategies that play into recognizing opportunities early on that maybe others miss?
Well, I mean, first of all, I echo what Professor Kulkarni has said. First of all, you have to enjoy what you're doing. So I was actually, when I completed my medical training, and when I joined Sir Weatherall's unit, he just said, well, I think it's very interesting that you should find out why some patients with beta thalassemia have such a mild disease, unlike the majority. And of course, when I started reading literature, there was already a lot of people who knew this, and they also knew that they were able to produce high levels of fetal hemoglobin. Then when I started collecting those families, the opportunity there was to understand how this trait was segregating, and people left it as that. And it was like solving a piece of puzzle. You know, I just collected as many families as possible. And then when you look at these clinical problems of families in front of you, just because you can't find it, it is there. You know, because the natures tell you that this is the problem. And then opportunities came and I could seize it in the sense that I started collecting a huge family, and when someone developed DNA fingerprinting probes, I could work within the work of the biological relationships. And then when I happened to know a very talented biostatistician who developed polymorphic probes, so I located the first kind of gene, and that gave me a lot of excitement and encouragement. Then again, also technology came at the right time. I met this biostatistician who developed another biostatistician, Canadian biostatistician, who developed polymorphic probes, and we applied the first kind of whole genome scan to locate this trait. As people often say, it's like needle in a haystack. And we found it.
So a lot of passion and a little luck.
Well, yeah, because, I mean, you can't deny it when you see it in the families in front of you. And this is what kept me going. There were a lot of skeptics, of course, to say, you know, we can't do it, but it is there.
Yeah. Dr. Orkin, you had said that you know, you had been studying this field for decades, and then there was about a decade period where your work had kind of stalled. How do you stay motivated through a period like that? What kind of advice would you offer for people who kind of face similar dilemmas in their own work?
Yes, in this field, we made some early advances, but then for a period of about a decade, I would say, really had difficulty getting to the next step. I think we're okay. What I try to do is keep my eye on the goal, but be curious in the interim when one is blocked. But I think one message that I think we've recognized, I think one message that's come through in my own experience has been that new technology really drives discovery. At least in the biological sciences. In my own career, we've seen the introduction of cloning, DNA sequencing. These seem, you know, like old hat, but they were discoveries at one point. Stem cell biology, gene editing, now introduction of AI into biological sciences. And I think each one of these provides really a way to get to the next step. And you have to be, I would say, in the right place at the right time to know how to take advantage of these advances and bring them to your own problem. And so I like to sort of keep my eye on the target, but have fun while we're doing the work.
Good advice. I want to switch now to the topic of collaboration. I know science is perhaps more internationally collaborative now, thanks to technology and things happening in the world today than ever before. Dr. Sarnak, maybe I'll start with you, because there's an idea perhaps that mathematics can be this kind of a solitary field. But you've also you've mentioned the crucial role that your peers have played in your work. I believe you mentioned Alexander Gambard, Jean Bourdain. How do you think we can foster these types of environments that encourage fruitful collaborations, especially in more theoretical fields like the one you work in?
So, as you say, people think of mathematicians as working by themselves, and that you do a lot of work by yourself. You have to suffer through understanding and misunderstanding understanding, and then gain an intuition, and that often can only be done by yourself. However, collaboration is absolutely critical. Collaboration. I've been in this business maybe 40 years doing mathematics since I started, and 45 even. And at the beginning, most math papers were single-authored. Today, most math papers got 3 or 4 authors. So I've seen this evolution of collaborative working. Of course, working collaboratively in mathematics allows different people to bring different skills to the table so as to achieve things that individually you might not be able to do. It also allows you to, if you have very good collaborators, you sort of understand each other very well and you get the best out of each other. And for me, collaboration has been absolutely critical. You mentioned John Bourgain and Alex Gumbert in this particular work that was cited in the Shaw Prize. This was collaborative from the beginning, very joint work, each person contributing decisively to different aspects of it. And how do we foster it, was your other question in this environment. I think mathematicians have now recognized the importance of collaboration. So the workshops that you have around the world and seminars around the world have been extremely important, and young people should do their best to come to these because these workshops are set up so that young people come. And collaborations start there. So somebody might be giving a lecture and you go and ask a question and quickly you realize there's something in common there. In the past, before all the technology of Zoom and so on, that was really critical. Now it's still very critical because one-on-one on the blackboard, that's how we work. One can really quickly get to the point. And I think probably in Hong Kong, certainly true in the US and Europe, they put a lot of, the governments put a lot of resources into this. And the mathematics that has come out is, you can see the results of it, outstanding. So it, like other sciences, mathematics is evolving to be a bit of a laboratory science in that way without having a laboratory.
Dr. Kulkarni, your work has kind of really leveled up collaboration in your field. You've collected mass amounts of data, made it almost instantly available to researchers around the world. How do you think we can encourage more of this kind of data sharing and collaboration within the scientific community, and especially given the sometimes competitive nature of research?
Yeah, okay. This is an argument and a discussion we had in our group about 10 years ago. Because the last project that I've done, which is I've been recognized primarily by the Shaw Prize here, is the Zwicky Transit Facility, which is, I think, still the world's largest camera, very sensitive, and we survey the sky every night, finding and trying to find things that change, move, whatever. And it takes money. It takes talent to bring all this together. Okay, so building the camera alone is $8 million. Refurbishing telescope is $4 million. Software system another $8 million. So we're talking by the time this is all done, and just in the sheer engineering side, 30, 40 people, then another 40 or so researchers, postdocs, students, people around the world. However, I realized, because this is the third phase of a project, smaller project I began 15 years ago. There's a tension here. If you invite people to contribute money and time, and they expect something special out of that, naturally. However, there are 2 ways to shine. One, you can shine by yourself, and you can also shine by reflected light, which I call as a halo effect. So I convinced our team that what we should do is we should set forth with what we want to do, because the machine we have built is extremely powerful. And so we do what we want to do, and then put the rest of the data out to the whole world. And that bet paid off. Well, there was a lot of discussion about, as you correctly pointed out, it's why am I spending the money in my university and then all these other guys are writing these papers? Fair enough. But to think slightly more like a business person, this is building up a brand name, ZTF as a brand name, if you wish. So we went the opposite way. We said not only we'll put the data out, we'll put it out in real time. So there's a whole worldwide network of consumers, what they're called data brokers, who actually analyze this data and then do whatever they want to do. So in about 6 years, ZTF team as a whole has published 200 papers, which is pretty good actually. That means in the team, someone is writing a paper every 10 days. Whereas the rest of the world has written 800 papers. So our halo effect is very large. And I think those concerns of us being scooped, yeah, once in a while it happens. And I think this is the future because not just in astronomy, but in biology, these are the two subjects. These are very large data producers. And the reason is not because they set out to do that, it's just the machines are capable, that's all. And would you rather just have your data be in a dustbin somewhere or get some papers and get some credit? So in astronomy as a whole, this has changed. And many space agencies and so on, they have actually decreased the so-called proprietary period where the countries which built and the PIs who had very special access is decreasing now. And mainly because the data has become so freely available, the real value now is what is the thing you really want to do with it? It's your time, your brains that is limiting you. It's not the data anymore.
Right. I want to open this up to Dr. Thein and Dr. Orkin. I know you've spoken a lot about how sickle cell disease is actually a growing problem globally when people think of it as kind of a more limited, rarer disease. How has global collaboration impacting your work and this field in particular?
Do you want to take?
Well, first of all, it is considered as rare, but actually it is the common rare, if you like. And certainly, I think global collaboration is very important. But in science, as it were, you can actually delve into depth in an environment that can actually have the resources to do cutting edge. And then when you want to actually apply it, you have to collaborate with the areas where there are large population numbers. It's akin to like when you first do clinical trials, for instance. You do phase 1, you show that it is very promising. Then to actually, the next stage, you have to do randomized double-blind, but you reach larger numbers. And this involves collaboration with other centers, which is very important because first, it adds populations of different ethnic groups to validate the data. So I would say, to me, I think global collaboration is very important for a disease like sickle cell disease and beta thalassemia.
Right.
I would add to that I think in terms of this particular disease where there are 5 to 10 million individuals, depending how you estimate the number, most of the individuals who could benefit are in resource-limited or poor countries and have less resource terms of healthcare. I think in some respects, the international collaboration for this is almost ahead of us coming in the future, because as we learn more, develop more tools, develop innovative therapies, they're going to be applied first in the resource-intensive areas, but then need to be brought to the rest of the world. And so I think the collaboration part, in my mind, is in the future. That's a challenge, but it's coming.
So going to change things up a little bit again here, move into artificial intelligence, a big topic I think a lot of people here are interested in. It was not too long ago that a lot of the ideas that are being put into artificial intelligence were also considered kind of more theoretical, and now it's having a real impact, I think, in all of your areas. Dr. Kulkarni, I know since you deal with a lot of data, large data collection, I'm wondering what kind of advances in computer technology, in particular AI, how have these improved the analysis and interpretation of the data sets that you're collecting, and what kind of impact do you see these advances having on your field?
Sure. So the phase one or the early phase pilot project for ZTF was Palomar Transient Factory, and which saw first light in 2009. And there are a number of people in the team, two people in particular, who had been exposed to machine learning, which I had not actually heard of at all in 2009. And I must tell you, I was very skeptical, okay, because it was early days, I would say. And so we had a very specific problem, which is what we do is actually very simple. We take a picture of the sky, let's say now, and I compare that picture taken some time ago. And there's a bit more than that, but I compare the two and see if there's a new object, okay? But when you take these two pictures, which are almost perfect data, and you subtract, subtraction generates artifacts, because they're not, so perfect minus perfect is imperfect, actually. And your human eye is very good at saying, oh, that's an imperfect subtraction, and that's a perfect subtraction. And so we had citizen science doing this classification. The humans can learn this thing in 15 minutes and do it very quickly and with high degree of confidence. So I told one of my colleagues who was in charge of this, said, prove to me. And we ran this side by side for a few months, and I got convinced. It wasn't as good as humans, but the machine learning algorithm really was working and took the tedious stuff. And then I became a convert. I'm a very practical guy. If it works, yeah, it's fine. And then the data, as we went through the next two phases in ZTF, the data flow has been increasing exponentially at this point. But our ability to digest, and my brain is decreasing, not exponentially, but it's decreasing. So for me, this has come at the right time. Right now, we are almost at the verge. In fact, we proved last year we can go from totally automated data collection, that is, the telescopes are self-sequenced. We don't sit there and say, oh, go and do this. It's a thing, we write an algorithm which says, do this for the next month in whatever way roughly you can. Even if there's a cloud, shut down, do whatever. Data reduced in real time, that's just algorithms, okay. But all the ranking, we are talking of 1 million events that are happening in a night, and in the end, we want to maybe study at best tens, okay. All that relative ranking, then which you pass on to something else to do some detailed studies, then to something else to do some other detailed studies, where the penalty of making a mistake starts increasing as you ask someone to do more work for you. Once in a while, it's okay, but not routinely. All that is now being farmed off what used to be machine learning, and now it's AI. Okay, so we are able to now go through this whole process without a human in the loop. And for me, that's fine. That's progress. That's wonderful, because my job is to go discover the universe, and these are tools. So the tools been great, and the other good thing is the students and postdocs working in this project, it's good or bad, I don't know. Anyway, they finish up and there's a tussle. They usually get all of them are very bright. They get a fellowship in astronomy, 70, 75K a year, and then Google or some startup will offer them 300K. I consider that success too. So either way, this is winning.
Yeah, so I think a lot of people are excited about how it's being used as a tool in these kind of real-world practical areas. But Dr. Sarnak, I know you have some particular ideas on or thoughts on AI in the more theoretical field. Do you think there's a prospect that AI, or in what ways do you think AI will be contributing to the more theoretical fields? Like, will we reach a point at which the technology as we know it could possibly be solving mathematical problems that humans can't?
Yeah, this is one of the most important questions that many mathematicians are asking, is what will the impact of AI be? Now, there are different parts of AI. Machine learning is really about data and statistics. And we don't want to know in math what is probably true. We want to know what's true for sure. So saying something is probably true, which is what statistics might suggest, is not something that I would see to be very useful in theorem proving. However, in looking for correlations that we haven't seen, in suggesting all the best conjectures in math were found numerically and discovered by practical computations by hand at first, later by machine. So I'm sure in that aspect, you're going to have machine learning play a very big role. I think it's going to impact mathematics dramatically more than that, especially certain parts of math are more amenable to case-by-case analysis where, and data kind of features that will mean that a mathematician, and this is a question that young people have to ask, am I going to come into the office and sort of hook up with a machine and work together with a machine as I try to prove a theorem? But to me, the biggest fear is that there be some situation where there's some proof, maybe of a problem that I'm desperately eager to prove, or many people are, and there's a proof that's 1,000 pages long, which a machine says is correct, and nobody can understand it. When math, I think everybody who goes into pure math at least, it's about understanding. It's about understanding why it's true. If that's lost in math, I don't know if it's mathematics anymore. So this is something we're grappling with because it's clearly on the horizon. It's clear that some aspects of being a professional mathematician, you will be at a disadvantage if you ignore it. It's interesting that the mathematicians are the last to really be picking this up, even though they should maybe be in the forefronts. But I think with the machine learning, it makes sense to me. Let me give one example, if I may.
Sure.
I used to be a professional chess player as a kid. And when the chess program started to beat people in 2000, when Kasparov lost to Deep Blue, didn't bother me one iota because the program was playing and explaining to you why it was beating Kasparov. It was calculating better, but if you asked what is the best move in this position, it would tell you, and then it would tell you why in terms of chess theory. AlphaZero beats all the computers and everybody, and it will tell you what the best move is in some position, but not be able to tell you why it's the best move. Mm-hmm. And then that's frightening.
Do you think it eventually will be able to tell you why?
Well, that's something you have to, that many people who work in that kind of AI are now interested in trying to understand what it's telling. But in the end, say with machine learning, there's some formula deep down in some deep learning program which is statistically analyzing things. And maybe really what a good chess player is recognizes positions in some statistical fashion to make a good move. That's true in chess. I think math is at a different level. Yeah. So I'm pessimistic about the big ideas coming from AI, but I'm 70 years old.
Well, on that optimistic note. So healthcare is kind of a different area, different space. It's highly regulated. A small mistake in healthcare can have big repercussions. I'm interested in what both Dr. Orkin and Dr. Thein have to say about what should we be looking for, what concerns should the scientific community have when deploying AI in, say, a laboratory setting or, in the work that you do. I know you're both pursuing drugs that could help with sickle cell disease. Is AI working in this area, and what do you have to look for? What are the dangers here?
Yeah, I think for AI and healthcare, one obvious question is whether AI or computers going to replace the doctor in terms of diagnosis, and does the doctor have value above the computer? I won't deal with that one. From the research aspect, in our own research, AI is really having tremendous impact right now, because what we're interested in doing is taking the very deep mechanistic understanding we have now of how the genes are regulated, and particularly how they switch from a fetal to adult is regulated. And what we want to do now is develop a pill, a small molecule based on that knowledge that could then be distributed worldwide for treatment. And we know exactly what the predicted outcome would be if we have the right pill. And we know the right target because Swee and I have worked on this gene B11A, which is the primary target. And what we're using AI for now is actually dissecting some structures of this protein using AlphaFold, which I'm sure everybody's heard of, recently honored with a Nobel Prize, because that helps us get a picture of the protein. And I think where AI is going to have an enormous impact, and it's just going to be the next wave, is developing tools that tell us, well, what chemical structure do we now want to put into that protein? Right now, that has to be done more or less by trial and error with chemists, some computational work. But I think if AI can give us the molecules straight off that we can then test, it's going to accelerate that work tremendously. So that's sort of what we're excited about, and we think the developments are just, again, right on the horizon.
Well, I think from healthcare, AI also has a lot of, it's already making an impact. Mm-hmm. Its real potential has not been realized yet. But the thing to remember is that it really depends on the data that you put in. So, let's say you wanted to help analyze data, but the data we put in, if it is mainly from people of all European origin, say genetics data, then it will interpret it in terms what is relevant for someone of European or Caucasian origin, but that would continue the bias and discrimination, somebody of African origin, for instance, where we don't have data from people of African origin put into, you're training it for the AI, that's one thing. But it has tremendous advantages already, say, for the use in radiology and pathology. It can analyze a lot of images that the naked eye cannot. For me, I found it very useful for the machine learning part, because one of the things I've always been interested in is to be able to predict the disease severity in patients with sickle cell disease and beta thalassemia. They're all caused by mutations in the same gene, but their patients have varying levels of severity. And if you can predict somebody who's going to have a severe disease later on, then it might be good to intervene earlier before all the damage has occurred. But you want to have confidence in aligning it with high-risk treatment.
Right.
And I'm applying it to one of the things that, of course, I work with people who are good at machine learning and predicting someone, a patient with sickle cell disease, who may have how well to do after bone marrow transplant, and use the risk factors to be able to predict who we should really be looking at.
Yeah, that's great. It actually sounds like there's a lot of, you guys are talking about a lot of promising things here. I want to wrap this portion of our talk with kind of another general question regarding AI for you guys, and then we'll open it up to audience questions. I'm sure a lot of people here have some burning questions for you. So just want to end on a piece of advice that you guys might have for how can we equip the next generation of scientists and researchers to succeed in a future that is going to be increasingly shaped and influenced by AI? Maybe we'll start from this side.
I don't have any good ideas. I was hoping you'd start on that side.
We can.
Yeah, start.
To me, it's very simple. It's how to put it, there was a time when calculators were not available, and it was a question whether you could go to an exam. The first question the students wanted to ask, can I bring a calculator or not? No one asks that questions anymore, okay? So,
Of course not.
so, yeah, I grew up without a calculator, and for me, computing in head is important, all the numbers, so I know that times table. So I consider it a weakness that you need a calculator, and Peter would agree with that because we're similar age and probably similar background, I suppose, in this respect. You know, I don't think, it's happened, it's a tool. It's like cell phones, you carry it around, it has some consequences, but it's a massive tool, it's demonstrated. And I feel that our graduate students in our program, in fact, we were discussing this, I was saying, no, we should actually teach them, we should actually have a course that equips them for the modern times, okay? As an example that perhaps Peter may like, when I was young, I really was very proud that I could, and I think I can. You give me any integral that's solvable in the real plane, not complex, and I claim it's analytical, I'll do it. But it's a useless skill. You use mathematics and you're done. So I don't think we should anguish much about this. We should just use it for what it is, which is a powerful tool.
Yeah.
Well, I think we all should learn to embrace it because it's going to be there.
Yeah.
And it should be, maybe in terms of medical curriculum, it should be introduced earlier. Just like when I was like teaching genetics, it was a ghast to find that it's not been introduced in the medical curriculum. They should learn to embrace it, and the students also learn to realize that it can also be, there are pros and cons, and not to also rely on it too much, to recognize its failures too, what it can do for you, what it cannot do for you.
I would agree. It's, you know, another one of these revolutionary developments that we should accept and use in our work. One has to, again, know what it can do for you and what it can't.
Yeah.
But we should use it to best advantage.
Yeah.
Okay, I'm ready to answer. I always encourage students at the undergraduate and graduate level to take physics, chemistry, and computer science because the connections between these fields, excuse me, are what inspire great math, and the interactions usually elevate both fields. And I think the case of artificial intelligence is just another, as has been said here, another very interesting direction that will impact math, and that people should be taking courses in that direction and maybe even thinking about having that as part of their arsenal of mathematical tools. I'm sure that in 50 years it will be a tool that every mathematician uses, no matter how they work.
Can I interrupt here? So if I have trainees coming to work with me, I mean, the opportunities for them, like courses, encourage them to attend a course on bioinformatics and learning about machine learning, not to actually, you know, be a specialist, but to recognize when they can apply it and collaborate with people who can use that tool to help them.
Great.
Very good.
Yeah. I think that's very, very useful advice. So now I want to open it up to questions. I'm sure I can already see people jumping at the chance to raise their hands. Yeah, let's. We'll start from the audience. We have some questions from. We'll open up to the audience and questions from online viewers as well. But start over here.
Thank you. I'm Qingfeng Jiang from the University of Hong Kong. And I have a question for Professor Kulkarni. And I have the privilege to work at the Caltech Astronomy and Planetary Science Department in 2022 and 2024. But I never imagined that the first time that I meet you in person is in Hong Kong. And you know, today's academia is becoming more and more competitive, and the slots are limited, and we are recruiting the most talented outstanding candidates from the graduate students or the postdoc scholars. And I'm still on my path in discovering who I am. So for our generation, in our first 10 years in academia, especially in astrophysics and planetary sciences, what thing do you think is the most important in our early career? Or what skills do you think we need to focus on to acquire to be more competitive in our future career? Thank you.
Okay. I would say that astronomy has undergone a really, really big change over 30 years. We have gone from a data-limited field where you would go, the opportunity or the quantity of data and the opportunity to get data were limited. You get a few nights of telescope time, you study a few objects, you came back literally with a magnetic tape so big in your hand, and then spend the rest of a year or two to write a few papers. The field is really exploded in data, and many agencies have made it a point of actually putting out curated data. So I would imagine for many people, many research in astronomy, having the skills and tools and also the understanding of how to exploit these large data sets would be very productive. Having said that, if you're not the sort of person who doesn't want to do that, you shouldn't do it, I'm saying. But I would say for 90% of the astronomers, this is where the bulk of the research would be happening. And people like me who have sort of been data generators, I think will decrease in time because I don't think the world needs that many data generators given this data explosion.
I saw we had a question over here. Yeah.
Testing. Thank you so much for all our Shaw Laureates for such a insightful sharing. So I am an undergraduate student. My name is Ariel from the University of Hong Kong. And there's so much pressure for writing proposals for funding on high-yield science topics that are more guaranteed to have more impactful results when such straightforward directions might actually be limiting advances in science. And in addition to the fact that we are in a system where accomplishments are tied to the number of papers that you publish, how is it possible for us to maintain the mindset of basic science ideology of researching for knowledge? So that is my question. This is just a general question for all our laureates. Thank you so much.
Any answers?
A very loaded question.
Sure, maybe rephrase.
To clarify, so I'm just asking that, so now that I think funding is definitely an issue in the science industry, and a lot of the funding is very based on high yield results. So they only allocate funding for studies that show to have high yield. But in the past, we have a lot of big discoveries that are based on chance or just not very straightforward. And also in a system where everyone is encouraged to publish as many papers as possible. How are we able to maintain the very basic idea of science, which is just researching for knowledge, when there's ideas of funding, we need high yield science and etc. I hope that clarifies a little. Thank you.
Is this about, say, the role of funding?
Yeah. I mean, my recommendation to trainees is always do what you think is interesting, and obviously with advice and careful thought, and at some point assume if you do it well, someone will support it, and you'll be able to move forward. Now, I recognize that in a time of limited resources, it's difficult maybe to follow that kind of path. But I think it's not the quantity of papers, it's the quality of papers that makes the difference. And so I would still focus on finding an interesting question or question you're interested in, getting the training and the tools to address that problem, tackle it, and go forward. I'm not sure I have a better recommendation.
Well, in math, funding is not as large as in these other fields, but it's still very important that you get funded. Otherwise, how do you continue and you want to have a job and so on? So your question, I think, is extremely important because it does reward research which is a little more, you know exactly how to solve the problem before you even start, and discourages very work that would come to an end. And so what I advise some young people, because if you don't have many publications, you're at a disadvantage, is if you work collaboratively, you usually can write a good number of papers that will keep you in the game. But the most important thing is what he said, is you've got to follow what you want. You have to leave your mark. You have to believe that you have a mark to leave. And to do that, you really must follow your own intuitions, and you build your own intuitions and your own understanding. So you must be very willing, and I'm talking about in math, to make mistakes, because the mistakes are what teach you how to proceed in other situations, and it may come back later, oh, I made a mistake there, but that's exactly what I need here. So you must follow your heart, and we all say that. But I think in this practical world, and it was not something we had to face, because I mentioned before, most papers were authored by one person 40 years ago in math, and most people wrote very few papers. But the depth of the paper was important. Today, with all these citation indexes and so on, it is a problem, and you have to be practical as well. And so you should sort of divide your time a little bit. Get some stuff out that is maybe a little more routine, but not at the cost of thinking deeply about what you want to think about.
Can I just add? I'll give a somewhat different answer. You're starting with a certain view of how science should be done, that people get into science. I'm being a little dramatic by saying, it's a noble thing to pursue. There's an ideology, that's the word you used. I guess you meant more like closer to an ideal. I have a different view. I think science is like any other activity in life. There's a game. It's an intellectual game. There are rules of this game, and if you're smart, figure the game and maximize it. Okay, so it's not like, oh, in the past that people could publish fewer papers, there's more money. That's a myth. The very few things in life change. In the past, if you go 20 years ago, a young person does the same thing. Maybe I would have said the same thing, and they go 20 years ago. So science, arts, these are all pursued under limited conditions. Many of us want to be artists. Many of us want to be scientists. Society doesn't have the money to fund all of us to do all pet things. And so there are demands on excellence, there are demands on productivity. On the whole, in well-run countries, okay, this is a fair process on the whole, in the average. Peer review is not perfect, but on the average, I would say it is. Many of us tend to remember, oh, I got dinged because of something. We never remember the occasions when you did get the proposal. It's a very peculiar thing. We tend to remember grievances more than successes. So I would take a different view. Take a brave view. Assume it's not as like what you're thinking, and say, here's a game. What are the boundary conditions of the game? And if you're smart, the more you optimize, the more you win.
Well, I have a different viewpoint. Well, in the sense that I think most of us agree that we all have to enjoy what we're doing. And the thing is also, there will be some high-risk projects in the sense that you will be trotting a path that nobody has done. But you're convinced that this is a very good idea. But, as you pointed out, we all have to survive. We all have to publish. So the high-risk projects, probably you will do it, you'll keep it in the, but you should also have some pot boilers that you can work with collaborators, that you know you can get some papers out. Meanwhile, you can pursue your high-risk project, and when the right time comes, opportunity comes, you can seize upon it. And it may be technology that is holding you back. And don't do a project simply for the sake that it is going to get you a paper.
Well, great. I want to get to a question over here, and then we have some interesting, very specific questions online. But first, let's start over here.
Thank you so much for the discussion. My name is Chiamaka Ngbechidimalinda. And I'm a PhD student from the Chinese University of Hong Kong. So it's nice to be here. So my question goes as such. Please, how do we, as young scientists or researchers, know that a research question is actually ideal and is groundbreaking? Because I would want to believe, based on my experience with listening to you, that a good question actually makes the path for a career goal and for novelty and for being who you are today. So myself, I look forward to being someone like you in the future, having given so much to the community. So how do I identify a good question that could lead me to that path? And my second question goes specifically to our distinguished laureates with respect to the gene editing and cell and molecular biology. I'm a student of that, so I would want to ask, based on the various techniques which are being poured out today, like we have the cryotechnology, bioinformatics, machine learning, we have single-cell sequencing. Which of these do you think would lead the path for the future research? Thank you.
Well, first start, I think to actually pursue a technique itself is not a good idea to start a research. You have an idea, you have something you want to address. Then you use those techniques to help you answer that question. And also to bear in mind that you can never be a master of any of these techniques because it evolves so quickly. So it's good to look for somebody who is good at that technique. And that person who's developing that technique will be so delighted to have somebody that will apply an idea for his technique. So as to ideas, you have to look around and you read, and then when you see around you, then if you have a mentor, you can also say, well, I have this idea. Do you think it's completely pie in the sky, or do you think it is worth, pursuing this idea? So that's kind of my thought to your question.
Thoughts on that?
Yeah, I think the second part of your question, I would say all the above. Everything you mentioned is important. With respect to the first one, the question students always ask is, well, what's the problem that's going to make me successful? Or whatever. And the problem with that is if we really knew that, all of us would be successful, I think. You don't know sometimes right at the beginning. It evolves over time as you get into something you're interested in. And if my recommendation is not to follow the herd.
Yeah.
There are many fads in at least the biological sciences. There are many areas where there are almost more researchers than patients to study if it's a disease, or more papers that don't advance the area. I always think you have to choose something that you're curious about that might be slightly off the herd, and then your challenge is to make that the herd that people want to come to.
We have interesting question on AI here for Dr. Kulkarni. Do you think AI can help overcome natural barriers for observations, such as observing UVC and UVB?
UVC, oh, okay, I understand. Yeah, so UVC and
explain,
UVC and UVB is the two ultraviolet bands that prevent us from observing ultraviolet from the ground. So the atmosphere is transparent up to maybe 30 to 50 angstroms, and it's a technical term, UVC, UVB. I don't think so. This is a physics effect, okay? There are molecules in the air, in particular, this is ozone, and that's the reason we don't get UV on ground, and those photons are lost. So I don't think you can AI may be powerful, but it's not more powerful than physics.
Do we have any other audience questions? Okay.
Couple hands up there.
All right, lots of interest here. Well, let's start with the young woman over here.
Good afternoon, everybody, and thank you for coming to talk with us. I have a question. I'm Sienna Lam from Hong Kong University of Science and Technology. I'm a fourth-year undergraduate student. I have a question for Dr. Thein and Professor Orkin about the gene editing. So I know somebody who has aplastic anemia. So could it be potentially possible to use a similar technique with the gene editing or some sort of analogous technique in order to cure aplastic anemia, like analogous to the technique that you are pioneering for sickle cell anemia?
I think with aplastic anemia, there's so many causes from the aplastic anemia. You could find out this gene editing. We know there's one simple gene, and we know that editing that gene can actually increase the level of hemoglobin to compensate for that abnormal or inadequate hemoglobin. In this case, with aplastic anemia, I would have thought a more traditional bone marrow transplant might be more useful.
Okay, thank you.
Yes, there are causes of aplastic anemia that if you knew the gene, you might be able to correct the gene and solve it. But really, bone marrow transplant is the standard care today.
I saw a hand. Yeah, this gentleman over here.
Thank you. Just maybe congratulations to all of you that win the Shaw Prize. So, I'm the PhD student from Hong Kong University of Science and Technology, and also I'm focusing on the stem cell research. So, also studied biology. So, I may have specific question regarding biology. So, actually, like Professor Orkin and you, I mean, both of you are focusing on a translational biology study, right? Try to cure the disease, but actually, lots of the biologists like focusing on the basic biology studies. So, what do you think about like how we can balance these two parts, or how we can take the knowledge we learn from the basic biology to make it translational to the final medicine or like disease curing methods?
Yeah, actually, most of my career has not been translational. Most of it has been basic molecular biology and stem cell biology, particularly focused on how blood stem cells develop and how they make decisions about what they do. It's really the basic biology. The translational part is sort of the frosting on the cake for the work that we've done. So I think you need both. I think it's very important. And I think there will be many advances in stem cell biology, and particularly cell therapies that are coming, where one uses cells as therapy in many different ways. And I think that's
you choose the gene therapy, right? Finally, like
not only gene therapy, but cellular therapy, manipulating cells to actually do things biologically.
Well, I come from a different direction because I'm first a physician. And I see the problems in front of me, okay? And I actually like outliers, patients who behave differently from the normal. And then ask myself the question, why? You know, just even take a simple thing like beta thalassemia, where somebody who have only a single copy and should be asymptomatic, but then you see them, you know, with more severe disease than usual. The reverse would be somebody who should be very severe, but have milder disease, and then just teasing this apart. And now with all those tools available for doing all the genetics, and so many things has been revealed actually.
Yeah.
And you start being able to classify the disease, not just what we would call phenotypically, and you realize that underneath this is actually a whole network of molecular things that gives you the same kind of phenotype. And uncovering that actually makes you then dive into all the different pathology, and you open up a whole new world. That's why it becomes so fascinating,
Yeah.
biology.
It's more like it depends.
Yeah, so I would say my research would be like, you know, clinical observations, back to the bench, and then take it back to the patient.
Yeah. Agree.
So I start from the other direction.
From identify the disease problem.
That's right.
Go to the basic.
Yeah. But always maintain a very curious mind.
Yep. Yeah.
That's the secret of doing science, I think.
Yeah. Definitely agree. Thank you.
So yeah, we have more questions from online. Lots of questions regarding biology. One thing, we kind of touched on this before, but I'm wondering about specific ethical aspects regarding AI application. This person is wondering about AI in medical research, but I think the ethical question can be much broader as well. But maybe, is there anything specific that springs to mind regarding the ethical issues in the areas that you're working in?
Well, I think the first thing people think of is privacy. When they think of AI and large data, will their medical information become public? Will it be used in some way to their disadvantage? I think that's certainly one aspect. I think in terms of research aspects, I don't think the ethics plays a major role unless you're talking about, trying to design new, viruses, create harmful viruses from AI and new diseases. But I mean, that would obviously be unethical.
Yeah.
One aspect which I can see in medicine, maybe over-reliance. Then at the end of the day, suppose mistakes are made, who is going to take the responsibility? Is it the physician who is over-relying on AI to make the diagnosis?
Yeah, to be determined, I guess.
Yeah.
Unless you guys have anything to add, maybe I'll take another question here.
So, good afternoon, the Shaw Laureates. I'm a Form 4 student from HKTA Thein Memorial Secondary School. And as a secondary school student, I aspire to become a researcher in the field of life science. But I'm still finding the area to work on. So, esteemed Professor Thein and Orkin, as a distinguished researcher in your field, I'm really curious about what are the most pressing issues in your field and that really need to be solved in the coming future. Thank you.
Stu?
Well, if you're asking what are the most pressing issues in the life sciences, that's a pretty broad question. You could point to many different areas, and consciousness and the brain. Those are big issues. In terms of the kinds of things that I'm involved in, I think I think using really detailed mechanism, structure of proteins to develop new therapies which are really targeted and are superior in terms of their both efficacy and safety, I think would be a major advance.
We have an interesting question here regarding statistics that I think kind of speaks to this idea that we're in this kind of post-truth world. Says, the question is there really a science for data? There's a saying that statistics and data are like bikinis. What they reveal are suggestive and what they hide are vital. Are we being too positivist and rely too much on past data and trends to project in the future? I assume, in the fields that you all work in, you guys are solving very real-world problems. You can see the results of what you're applying. Do you have any response to this kind of view in terms of what we are solving for?
I think statistics, firstly, is just another branch of mathematics. The features that you look, the theorems that you try to prove, the central limit theorem, the basic things that are used in statistics and now in machine learning, that's mathematics. So it's a branch of mathematics, but the issue, I think the question there was its impact on the development of the subject more than just as a piece of mathematics. I should say that in the US, statistics departments and math departments are separate. I've never understood that. I don't know what's happening in Hong Kong, but in the sort of British system, they're in the same department, statistics, computer science, and that makes a lot of sense to me. The kind of difficult statistical mathematical problems are very similar to pure math difficult problems. Within math research, which is the only thing I have real experience with, the statistics and data comes from the objects we study, and we try to see patterns. And there, machine learning can be very useful. And that's something that mathematicians have done from the very beginning. They compute examples and look for what's true and then say, oh, this might always be true, and then try to prove it. And so it is become, I think, and I think there will be a tremendous impact, which will be much bigger than it is now, in terms of predicting. So mathematics has, pure mathematics has conjectures, and it comes with theorems, conjectures and theorems. The conjectures are extremely important. That's what drives, there was some question, what are the big questions? And in some sense, we choose them, which is a bit weird. But they are usually driven by the objects we're interested in and where somebody recognizes patterns. And I think it's this mixture is going to be very relevant, more for conjectures than for proving theorems. When it comes to proving, I still insist we have to understand.
Yeah.
Matt, I think there was...
Yes.
Yes,
time
that's
for
right. Keep on trying to ask questions.
Two more questions from the audience, and then we'll take two from online as well.
So thank you very much for giving me a chance to have a question. And it's such an amazing experience to hear from conversation between professor and directors. So my name is Lam, an undergraduate student from AKUST. And it's a question from Professor Sarnak. Yeah, nice to meet you. And as you have said, mathematics require understanding the concepts and the proof to know the relations. And for me, as a math major, at times I read a proof and I feel like I didn't very understand the proof. For example, like some definitions that are used in a proof, but directly implies to another abstract results, but which may not seem to be related to the theorem or the key point. And also when I'm experienced like some of the proofs, some same results, but in different notation, that takes me time to understand as well. So my question is that I would like to ask if when you read a proof, how can you deal with trying to use the knowledge to feel the connection when you struggle when seeing the problem to prove some term or proposition or lemmas? And the final one is when when you have said about the machine learning, I would like to ask when what's the type on which content that machine learning can support your situation on understanding the proof. Thank you very much for your support.
Okay. There are a lot of points you made. Let me address at least one, which I think is very relevant to you. Often you're taking a course and you see a theorem presented to you. It's usually very slick, clever. The instructor is trying to show you how beautiful it is. That's the finished product, and you look at it and you say, I couldn't come up with that. And you probably couldn't because it evolved through many years. So my advice in learning any kind of new theorem or new thing that you're not familiar with is to go to the source of where that was invented, where it's dirty and messy. And you read the original, and then you read how it got to the version that you're reading now. And then you'll quickly see that, oh, that makes much more sense, and you yourself might have. There's going to be those steps that are highly inspired that very few people can come up with. But the part that understanding a proof by looking at it at the end is what makes it kind of frightening, and it's easily best overcome by going to the beginning. So you should go to the original source, which might be, you should ask your instructor, maybe there's some good account which discusses it as it evolves. So for me, the way math evolved is a very big part of the way you think. And it'll help you, I think, bring it into your own system. I think, let me answer that much of your question.
So thank you very much.
We have time for one more audience question. This gentleman, sorry, I saw, yeah, your hand first. Sorry.
Thank you. I'm just a member of public. How would you visualize the value judgment or the ethics issue for AI coming to existence in the future? How would you visualize about the AI? Especially about the value judgment. Thank you.
Is this a separate question from, I mean, we touched on the ethics of AI.
The ethics is just privacy or the responsibility. What I mean is when the AI is being sensible for his own value judgment.
Value judgment?
Yeah. The AI that can something, maybe I don't understand if what the expert that can inspire me to think about that the future, the trend for the AI that will.
I mean, will AI be making value judgments
yes.
in the future? Yeah. I think we touched on that briefly. I don't know if you guys have any thoughts on that. This might not be the right forum for that particular question. Maybe I would like to, maybe if there are other students here who are eager to ask a question, in the back here. We'll take one more from the audience.
So thank you all for your inspiring sharing. So I'm Warren from St. Paul's College. I'm a high school student. So currently, I would like to ask a question to Dr. Sarnak. So I'm interested in like mathematical Olympiads. So when I look at your like research, you attempt to link like between number theory, geometry, and combinatorics together, which in mathematical Olympiads, they don't really come together that often. So, like, my question is that, what inspires you to research between their linkage, and how, as a high school student, which only has a limited understanding in pure mathematics, how can I start to understand, where do I start to begin to understand your research? Thank you.
Well, firstly, kudos to you that you are good at these competitions. It's not necessary nor sufficient to be a mathematician, but it's a very good sign. These high school competitions, I think, they bring out certain parts of mathematics, and the connections usually come after you understand much more. So my view is that you should learn the basics. So for example, if you're taking undergraduate math, I'm always insisting, as I said earlier, that you take computer science, physics, because those connections you'll only be able to make if you understand what's basically in those fields. So you take these different fields which often were invented to try solve the same problem and then became fields of their own. So it's not so surprising in the end that they become connected. But in order to see that, you have to have a good feel about each of those, and that you learn as an undergraduate, or maybe even in high school, but as an undergraduate. And then when you get to graduate school, you have these basics, and I still insist on continuing these different directions, not completely different. And the way they get connected, of course, when that happens, is rare, but when they do get connected, it feeds off each other very well. So it's only by being knowledgeable that you can make these connections. And I should say, in the last, some of the greatest theorems proved in the last 100 years connected fields that people were completely blown away by. So probably one of the greatest theorems ever proved in math is due to a Russian mathematician, Perelman, who proved the Poincare conjecture using nonlinear partial differential equations in physics. So it is the way the subject has evolved in its most impressive way. But in your position, read good sources, as I was saying before, go to the original. So you read, try to read good treatments of geometry, number theory, and that they connected is what drives, say, much of modern mathematics. The Langlands program connects these things. And as you study, you'll be able to see this connection. You shouldn't feel that you have to see it immediately. Yeah, let me see. Okay.
Great.
So in other words, get those dots and then they will join up eventually.
Correct. You have to.
So we're way over time here, but I want to wrap up with one more question from online. This one is about burnout. With students exhausted by academic competitions, how do you maintain a balance between your research and leisure time? I think leisure time is quite important in research. It's stereotypically when you have your eureka moment, I think. So how do you strike this balance? Maybe we can go around. Start here.
Yeah, well, I would say this is a very important question because when you're young, you're very ambitious, you want to do things, and burnout is almost inevitable, I would say. It's only a question of when for most people. So I always advise my graduate students that they should really maintain a very rigorous practice of physical exercise, either jogging or gym, and meditation. I think it's very important. So in your rush to fame and productivity, don't forget to take care of your body and your mind. And I wish someone had told me this when I was young.
So I would love to know how to meditate. Can I join your class? There's something I could never master, meditation. I know it's very good for the mind, but I agree with you. I mean, taking regular exercise is very important. And main thing is also enjoy what you're doing. Then it becomes a hobby. And to read widely, not just science.
Okay. All the disciplines.
All the disciplines. I mean, I, for instance, love reading biographies because I love to know what made people stick. So.
Yeah. Thoughts?
I agree, but I would say that the work is important, what you do, but it's part of your life, and there are other parts of your life if you want to feel fulfilled in what you do.
I agree with that. I exercise or I think I exercise, I should say. Many good ideas, many of your best ideas do happen when you are not thinking directly, but thinking about something else, and all of a sudden something comes along. And that often happens during exercise. Burnout, I don't think that, I think we've emphasized, burnout means you emphasizing that the success of doing whatever you're doing is to be the best in the world. That is not the attitude you should ever take. Yeah. If you get lucky and fortunate enough that things fall together and you're the right person at the right time, that's great. But you should really be doing what you enjoy, and you should be trying to feel that there's something that you have to say that you can add to the subject, whatever the subject is. And say if you do a PhD in mathematics, does not mean you have to be a research mathematician. You've contributed to math, you've shown that you can think logically in a very powerful way. And in fact, I think the math degree is probably the most employable of all these days. Everybody wants to hire mathematicians. So it's not, that never used to be the case, by the way. Mathematicians would just look at their shoes, right? But now, so I think that the emphasis, burnout means that the only aim is to just sort of be the absolute best. No, you can be very good. This is what's wonderful about research and academia, is there's a lot of room for quite a few people as opposed to being a chess player.
Well, I could add one thing, which is it's about 6-7 years ago, I was running Caltech Optical Observatory. It's a very big enterprise, at Palomar and in Hawaii, and then we're building a 30-meter telescope, which is a $3 billion project. So there's a lot of running around. And meanwhile, I'm still teaching because that's necessary to be a professor. And when I stepped down, I was exhausted, not really burned, exhausted. And then I decided I'll switch my career and I want to do some single author paper. And I discovered a secret. And then I went and told this secret to a very famous astrophysicist, actually one of the earliest Shaw Prize winners. And he said, Shri, I knew this when I was 20 years old. I said, well, I guess that's why you're a bright guy. The secret is, I'm sharing that with all of the young people, is I really dislike exercise because I'm very active in the monotony of getting on a treadmill is very hard for me, extremely hard. So what I did, the secret is, since I switched subject to a more theoretical subject and was learning, all the basics, fluid dynamics, all this sort of stuff, I would get stuck in a problem, and I think about that problem, and I go to that gym, having written down 3 or 4 problems that I'm stuck on, and then I just sit and think about this and just get on the treadmill, and after about 20 minutes, A, it was done, and B, actually, many times I found I was actually solving these problems. And so my theory, I know I'm not a biologist, is I think there's some blood flow, brain gets better. Anyway, so I suggest you do this. You get both things done. Problem solved, body solved.
Well, great. I hope everyone's inspired to take better care of themselves. I know I am. I just want to say thanks again to everyone for joining us today, and congratulations again to the laureates on stage. I feel like this was a great conversation, and I'm glad everyone got to hear it today. Thank you.